In the previous lecture, we finished section 3.5. Now we have 3.6, which is about solving initial value problem and boundary value problem by using Laplace transforms. Here, in this section and in the next section, we use the Laplace transforms for solving ordinary differential equations. If you have given an ordinary differential equation, we can solve it by Laplace transforms. Here, we say in solving initial value problems and boundary value problems, we are going to follow these steps for solving the initial or boundary value problem. We first rewrite the equation in terms of Laplace transforms. That means we are going to take the Laplace transform for each term in the differential equation. Then we insert the given initial conditions. In initial and boundary value problems, we have to be given the initial conditions or boundary conditions. We insert them in second step. In the third step, we rearrange the equation algebraically to give the transform of the solution. We will write down the equation. Then in step 4, we determine the inverse transform to obtain the particular solution. We just follow these 4 steps. We first take the Laplace transform for each term in the differential equation. Then we insert the conditions, the initial conditions, and then we rearrange the equation such that y of s to be alone in one side of the equality and all the other terms to be in the right hand side. Then we determine the inverse Laplace transform for the right hand side to get the solution for the initial value problem or boundary value problem. Here we say if we have y of t, the Laplace transform of y of t is capital Y of s. Y of t, its Laplace transform is capital Y of s. And the Laplace transform of y prime of t, it is s times capital Y of s minus y naught. It's s times capital Y of s minus y naught. This is the Laplace transform for y prime of t, or dy by dt. The Laplace transform for y double prime of t, it equals to s squared y of s minus s y naught minus y prime naught. These two, this and this, are the conditions. And here, this is the condition that will be given. Then for the Laplace of y triple prime of t equals to s cubed y of s minus s squared y naught, s y prime, and then y double prime naught. This is how to take the Laplace transform for y prime, y double prime, and y triple prime, and so on. Okay, that's for y to the order n. Here you have an example. In the first step, as I said, we just take the Laplace transform for both sides. We take Laplace transform for both sides. Step 1, here we have given a differential equation with initial condition. This is y naught equals 1. This is y naught equals 1. Here t is 0, y is 1. Y of 0 is 1. This is the initial condition which is given for this differential equation. We are asked to solve the differential equation. It's a first order differential equation. To solve this, what we do, we first take the Laplace transform for both sides of the differential equation. We take the Laplace transform for dy by dt minus 2y equals the Laplace transform of 4. You should know what's the Laplace transform of a function. Okay, we talked about this before. And here we take the Laplace transform for dy by dt and minus 2y separate for each. This is, here we say it's the Laplace transform of dy by dt, it's y prime. Okay, this is y prime minus Laplace transform of 2y minus Laplace transform of 2y, it equals to the Laplace transform of 4. We say the Laplace transform of a constant is the constant of a t over s. The Laplace transform of a, it is a over s. Okay, that means the Laplace transform of 4 is 4 over s. And for the left hand side, we have Laplace transform of y prime and Laplace transform of 2y. Here we find the Laplace transform of y from this, which equals to y of s, and the Laplace transform of y prime equals to s times y of s minus y naught. The Laplace transform of y prime is s times y of s minus y naught. This equals to, here, the Laplace transform of y prime is s times capital Y of s minus y naught. This is the Laplace transform of y prime. Then minus 2, you have this 2, we take 2 out of the Laplace transform. Then the Laplace transform of y is y of s. As you see here, it says the Laplace transform of y is y of s. This equals to the Laplace transform of the right hand side, which is 4. Its Laplace transform is the constant over s, which is 4 over s. The Laplace transform of a constant is the constant over s. Now we leave all y of s in the left hand side and others to the right hand side. But before that, in step 2, we insert the initial conditions. Insert the initial conditions. Here we have only y naught, y of 0. Y of 0 equals 1. We replace by 1. Okay, we apply the conditions, we insert them. We have only one initial condition here, which is y0. Y0 is 1. We replace by 1. We get s y of s minus 1 minus 2 y of s equals 4 over s. It's 4 over s. Now, in step 3, we rearrange the equation. We write down a function for y of s. Okay, that means we leave y of s alone in the left hand side. Here it's 2y of s. It's s y of s. So we move this negative 1 to the right hand side. We move that negative 1 to the right hand side, because in that term we have no y of s, and you get s y of s minus 2 y of s equals 4 over s plus 1. We remove negative 1 to the right hand side, becomes positive 1. Now here we are going to find the common denominator. This equals to 4 plus s over s. Is it? It's 4 over s. 4 plus s over s. Now between these two terms, the common is y of s. We take y of s as the common. What's left here? You get s minus 2. That's s minus 2 equals 4 plus s dividing by s. Now, so this y of s. Y of s times s minus 2. If we take y of s as the common, we get s minus 2. And in the right hand side, we have 4 plus s over s. Then we say y of s equals 4 plus s dividing by s times s minus 2. It's s times s minus 2. Then to find y of t, we say the Laplace transform f of t is capital F of s. How about the Laplace inverse of capital F of s? This equals to f of t. Okay, And it's the same for y. See, the Laplace inverse of y of s equals to y of t. The Laplace inverse of y of s is y of t. So here we must find y of t. Y of t is the solution. To find y of t, we take the Laplace inverse for both sides. We take the Laplace inverse for both sides. For Laplace inverse for both sides. What we get? We get the Laplace inverse of y of s equals the Laplace inverse of 4 plus s dividing by s times s minus 2. Okay, now we say the Laplace inverse of y of s is y of t. Y of t, this becomes y of t. Because as you see, I have written down here. The Laplace inverse of y of s is y of t. It equals to the Laplace inverse of s plus 4 dividing by s times s minus 2. Here, since in the denominator we have the multiplication of two terms or two brackets, s times s minus 2. Here, in this case, we must use partial fraction. We use partial fraction for finding the Laplace inverse. I'm going to do the partial fraction here. We say s plus 4 dividing by s times s minus 2 equals to a over s plus b over s minus 2. Now we find the common denominator here, and we get a times s minus 2 plus b times s dividing by s times s minus 2. Okay, now in the numerator we have s minus 2, as minus 2 plus bs. It equals to what? Equals to this numerator here. This fraction equals to this fraction, so the numerators are equal. That means a times s minus 2 plus b times s equals to s plus 4. Here in this term becomes 0 when s is 0. We say let s to be 0, then we have minus 2a equals 4. If you replace s by 0 in the equation, we get here we get 0, here we get 0, this term becomes 0, and this becomes 0. So here we get a times -2 equals 4. That means minus 2a equals 4. And from this we can say a is minus 2. This is the value of a. Then to get b, we replace, we try to make this term to be 0. How to get 0 for this term? If you replace s by 2, if you replace s by 2, the first term, this term becomes 0. We let s to be 2. Then the first term becomes 0 plus 0 plus. If we replace s by 2 here, we get 2b equals 2 plus 4. And then here 2b equals 6, so b is 3. These are the values of n. That means this Laplace inverse equals to the Laplace inverse of a, which is not minus 2, a over s, minus 2 over s, plus b over s minus 2, b over s minus 2. You replace a and b here, and that's all. b is 3 over s minus 2. Now we take the Laplace inverse for each term separately. Okay, for the first term, it is for the first term it's minus 2 t, minus 2, sorry, it's only minus 2. It is minus 2 because here the Laplace of minus 2 is minus 2 over s. So the Laplace inverse of minus 2 over s is minus 2. Then plus 3 times 1 over s minus 2. It is the Laplace of e to the power 2t equals to that. So the Laplace inverse of 1 over s minus 2, the Laplace inverse of 1 over s minus 2 is e to the power 2t. Is e to the power 2t. So this is the solution for the differential equation. Thus, y of t equals minus 2 plus 3 e to the power 2t. This is the solution for the differential equation or for the initial value problem. Here, if you have given a differential equation, I want to solve it by using Laplace transforms. We first take the Laplace transform for each term. After taking the Laplace transform, we insert the conditions, the initial conditions. After that, we rewrite down the equation for y of s. As you see, this is step 3. We have written down the equation for y of s. Then we take the Laplace inverse for both sides. For the left-hand side, we have only y of s. If we take the Laplace inverse for y of s, it's y of t. And then we take the Laplace inverse for the right-hand side, which is a function of s. Here we use partial fractions for finding the Laplace inverse, and you get the result. So this is the solution for the differential equation. This is the solution for the differential equation. Do you have any question? We now have another example. It's a second order ordinary differential equation. Here we can solve any order of differential equation by using Laplace transforms. In the first example, there's first order differential equation. We now have a second order differential equation. We have given two conditions. Here it means y of 0 is 5. Y prime of 0 is 7. We have these two conditions. Okay. In the first step, as I said, we take the Laplace transform for both sides. We say the Laplace transform for the left-hand side is y double prime minus 3y prime plus 2y equals the Laplace transform of 2e to the power 3t. We take the Laplace transform for both sides. And in the left-hand side, we have 3 terms. We take the Laplace transform for each term. Then the Laplace transform y double prime minus 3 Laplace transform of y prime plus 2 Laplace transform of y. It equals to the Laplace transform of 2e to the power 3t. Now we take the Laplace transforms. We say the Laplace transform y of y, it equals to y of s. The Laplace transform of y prime equals to s y of s minus y naught. The Laplace transform of y double prime, it equals to s squared y of s minus s y naught minus y prime. Here we have the rules here above. Yeah, here we have these rules. I've just written down these. Now we take the Laplace for the terms. For the first term, the Laplace transform for y double prime is s squared y of s minus s y naught minus y naught prime minus y naught prime minus 3. This is the first one. Then for the second one, it is minus 3. The Laplace transform of y prime is s y of s minus y naught. It's s y of s minus y naught. And then for y, it's 2y of s equals the Laplace transform of 2 times exponential of 3t. We say the Laplace of e to the power at equals 1 over s minus a. And here we have 2 times this. We say 2 over that. We just multiply it by 2. Okay. Then the Laplace transform for the right hand side is 2 over s minus 3. Since here a is 3, a is the coefficient of the exponents, and that too is the coefficient for the function. Now, this is the first step. In the second step, we insert the conditions. We replace each y naught by 5, and we replace each y prime by 7. As you see, it's given. This is y naught, this is y prime naught. Okay. We replace each y naught by 5 and each y prime naught by 7. We get here the second step, insert the conditions. Insert the conditions. We get s squared y of s minus s times y naught. Y naught is 5. Y naught is 5. That means you get 5s. 5s minus y naught prime. Y naught prime is 7. Minus 7 minus 3 times s y of s. 3s y of s minus 3 times minus y naught is 3y naught, but y naught is 5, so 3 times 5 is 15 plus 15. Here we insert the condition and then we apply it by 3, by negative 3. It's negative 5. Then we multiply it by minus 3 is 15 plus 2 times y of s equals 2 over s minus 3. Now we have step 3. In step 3, we rearrange the equation. I write down an equation for y of s. First, we move all terms with no s to the right hand side. We move all terms with no y of s to the right hand side. Here we have, first let's simplify this. It's minus 7 and 15 is 8. When you move it to the right hand side, it becomes minus 8. So we get s squared y of s minus 5s. We move it to the right hand side, becomes plus 5s. There's 2 over s minus 3. When you move this to the right hand side, becomes plus 5s. And here we have minus 7 and 15 is 8. When you move to the right hand side, becomes minus 8. And you have no more terms to move to the right. We get minus 3y of s plus 2y of s. Now, between these 3 terms, the common is y of s. We take it as the common. We take it as the common. We get y of s. What's left? S squared minus 3 plus 2, which is 5. Is it? Here, 3y minus 3y of s and 2y of s. I'm just going to simplify it. Minus 3, sorry, it's s y of s. Minus 3 is y of s plus 2y of s. Yeah. It's 3s minus 3s plus 2. It's equals to. Here, in the right hand side, we are going to find the common denominator. So the common denominator is 2 over s minus 3 plus 5s minus 8 times s minus 3. Is it? So the common denominator here is 1, and that's s minus 3. The common is s minus 3. Multiply this term by s minus 3, and we write down 1 common denominator, which is s minus 3. And here 5s minus 8 multiplying by s minus 3 is 5s squared. It is 5s squared minus 15s minus 8s plus 24. Is it? Then minus 15s and 8s is 23s. So you get 5s squared plus. So you minus 23s plus 24. We get this in the numerator. It is 5s squared minus 23s plus 24 dividing by s minus 3. Now, we should leave y of s alone in the left-hand side. We divide both sides by s squared minus 5s plus 2. We divide both sides by s squared minus 5s plus 2. So y of s equals 5s squared minus 23s plus 24 dividing by s minus 3, s squared minus 3s plus 2. We can factorize this also. We must factorize the denominators. Okay, to factorize this, we get s minus 2, s minus 1. Is it? It's s minus 2, s minus 1. So we just replace this by s minus 2, s minus 1. Now, to get y of t, and now we are in step 4. In step 4, we take the Laplace inverse for both sides. The Laplace inverse for the left-hand side and the Laplace inverse for the right-hand side equals to the Laplace inverse of 5s squared minus 23s plus 24 dividing by s minus 3, s minus 2, s minus 1. Okay, we now try to use partial fractions for finding, for separating these fractions. We say, I'm going to do it here. We say 5s squared minus 23s plus 24 over s minus 3, s minus 2, s minus 1 to be equal to a over s minus 3 plus b over s minus 2 plus c over s minus 1. Now, to find the Laplace transform for this fraction, we cannot do it directly. So we use partial fractions. We say let it equals to a over first bracket plus b over second bracket plus c over third bracket. And since all the brackets are linear, we just say a, b, and c. We just use a, b, and c in the numerators. Now, we are going to find the common denominators here. And the common denominators is s minus 3, s minus 2, s minus 2. It's their multiplication. The multiplication of all denominators is the common denominator. And sorry? I didn't get what you say. Yes. Now we find the common denominator. Okay. Here we say s minus 2, s minus 1 multiplying by 8 times s minus 2, s minus 1. Okay. Then plus b multiplying by. We just multiplied by the other denominators except itself. Okay, except its denominator. S minus 3, b times s minus 3, s minus 1 plus c multiplying by s minus 3, s minus 2. Okay, we say it equals to, we try to simplify it. We say this equals to here s minus 2 times s minus 1 is s squared minus 3s plus 2. So it's a times s squared minus 3s plus 2. And b times s minus 3 s minus 1. That's s squared plus b times s squared minus 4s plus 3. And c times s minus 3 s minus 2 is c times s squared minus 5s plus 6. All dividing by s minus 3, s minus 2, s minus 1. We now say this fraction is equal to this one. And these are equal because we say this equals to that, to a over s minus 3 plus b over s minus 2 plus c over s minus 1. These are equal. So these are equal. Since these are equal and their denominator are the same, so their numerators must the same also. Their numerators must the same also. Here we say we multiply a to this bracket, b to this bracket, and c to this bracket. Here we get as squared, bs squared, and cs squared. Okay. Here when we multiply this to the first term, we get as squared. When you multiply b to the first term, we get bs squared. And when we multiply c to the first term, it is cs squared. This equals to a plus b plus c times s squared. Is it? And then when we multiply each of the constants to the second term, we get, we can take s as the common. We get plus minus 3a minus 4b minus 5cs. We take s as the common between them. Then when we multiply it to the third terms, a times 2 is 2a. b times 3 is 3b. Then c times 6 is 6c. This equals to what? Equals to 5s squared minus 23s plus 24. Here is. Here we multiply a, b, and c into the brackets. أقللهم a ضرب هنا كان يمكن a بشي as squared plus minus 3as plus 2a. وايا بو دوم يعني b ضرب هنا كان يمكن شو ما نذكر bs squared وانيا أقل c ضرب هنا كان يمكن cs squared ما نذكر وايا كاتل النيون أم سنة شو ما as squared هم bs squared هم cs squared هم أقل s squared بحاول شو يمكن شو من a plus b plus c. أو بو دوم يعني بو اس كاس بها بجوج ضربي ترمي دوم يعني اي ضربي ناقص اس بي ضربي ناقص 4 اس سي ضربي ناقص 5 اس دير اس بها بجوج شو معناته ناقص اي ناقص 4 ناقص 5 ان جاء ضربي يكون ساعتها كم اما دو اي هي ليره 7 هي وليره 6 سي اما كون ساعتها كان أما أوانك إس يعني قلاية أما أوانك إس يعني قلاية. Okay. We have two polynomials which are equal. We say the coefficients must equal also. We say a plus b plus c must equal to 5. Okay. Then minus 3a minus 4b minus 5c must equal to negative 23. Look, this is the coefficient of s, and the coefficient of s is minus 23. That's why we say it must equal to negative 23. And the constant terms, 2a plus 2a plus 3b plus 6c equals to the constant term here. The constant term here is 24. We have these three equations. We have these three equations. We can solve them and we can get the values of a, b, and c. You can use grammar rule for finding a, b, and c. After finding a, b, and c, just plug into here. Then we say this equals to the Laplace inverse of a over s minus 3 plus b over the Laplace inverse of b over s minus 2 plus the Laplace inverse of c over s minus 1. Just plug into here, then find the Laplace inverses. And all the Laplace inverses are going to be exponentials. Okay? So here I'm going to leave this for yourselves to find values of a, b, and c. It's easy, but it takes time. You just can apply the grammar rule for finding a, b, and c. After finding a, b, and c, plug into here, here, and here. Then find the Laplace inverses. So the Laplace inverse are, for this one, it's a times e to the power 3s plus b times e to the power 2a. So it's 3t, not s. 2t plus c e to the power t. Just find the values a, b, and c. Okay? See the Laplace inverse of a of s minus 3 is a times exponential of 3t. And the Laplace inverse of b over s minus 2, its Laplace inverse is b times a to the power 2t. Here, generally, we say the Laplace inverse of a over, let's say, g over s minus a. This equals to g times e to the power at. Okay, if g be anything, be any constant, we just write down itself, and then here a is the coefficient of the exponent for exponential function. Here I'm just going to leave finding a, b, and c for yourselves. This is how to solve a differential equation or an initial or boundary value problem by using Laplace transforms. So let's take a break. And the last section in this chapter is about solving system of differential equations by using Laplace transforms. Here in this section, we use Laplace transforms in solving system of differential equations. That means if you have more than one differential equation, it's called system of differential equations. Here we have two differential equations, this and that. Both together, each of these is a differential equation. And both together, this is called a system of differential equation. This is a system of differential equation. To solve this, we use Laplace transforms. We use Laplace transforms for solving this system of differential equations. Here, we take the Laplace transform for each differential equation. We have two differential equations. We take the Laplace transform for each, for both sides of each differential equation. So the Laplace transform for this one and the Laplace transform for this one, we get this. Okay, and you apply these rules. We apply these rules that we talked about here. We apply these rules. We say the Laplace transform of y of t is capital Y of s, or y, and even the Laplace transform of x is capital X of s. The Laplace transform of y is capital Y of s. And the Laplace transform of y prime is s y of s minus y naught. That's s y of s minus y naught. And the Laplace transform of y double prime is equals to s squared y s squared y of s minus s y naught minus y naught prime. These are for x is also true. The Laplace transform of x equals capital X of s. The Laplace transform of x prime equals to s capital S or capital X of s minus x naught. And the Laplace transform x double prime of t equals to s squared x of s minus s x naught minus x naught prime. Okay. In solving the system of differential equations, we take the Laplace transform for each differential equation. After taking the Laplace transforms, we get this. Here we have these two differential equations. This one, we have these two differential equations. The Laplace transform for the first one is this is dx by dt, that's x prime, and dy by dt is y prime. Here we have the Laplace transform of x prime equals the Laplace transform of the right hand side. In the right hand side, you have two terms. We take the Laplace transform of each term, the Laplace transform of x and the Laplace transform of y. Here, this becomes the Laplace transform of x prime is capital X of s, so s capital X of s, s capital X of s minus x naught minus x naught or x of 0 equals to 2 times Laplace of x. It equals 2 capital X of s plus y of s. Here the Laplace of y is y of s. This is for the first equation, and for the second equation also we do it. For the second equation we do it, and we get this. We get this differential, this equation. This is by taking the Laplace transform for each side of the differential equations. Now we rearrange again. We put all the terms without x of s and y of s to the right hand side. Here we have this negative one, we move it to the right hand side, but here we have 2x of s plus y of s, we move it to the left hand side. We move it to the left hand side. And here we have x of s here, and here we have x of s. We take x of s as the common, we get s plus s minus 2. X of s minus y of s equals 1. Here we move this negative 1 to the right hand side in the first equation, and moving these two terms to the left hand side. We get s x of s minus 2x of s plus minus y of s equals negative 1. So equals plus 1. When you move negative 1 to the right, it becomes positive 1. Now between these two, x of s is the common. What's left? S minus 2. So you get s minus 2 x of s minus y of s equals 1. This is the first equation. So the first equation becomes this. Now for the second one. For the second one, we do the same. Here you have no terms without x of s and y of s. We move these to the left hand side, and you get s y of s minus 3s y of x of s. 3x of s. It's minus. When you move to the left, it becomes negative. And 4y of s, when you move to the left, it becomes negative. Minus 4y of s equals 0. And here you have two terms with y of s. We take y of s as the common, and we get s minus 4 y of s minus 3x of s equals 0. We now rearrange these two. We write down x of s beneath each other and y of s beneath each other. Then here we have two equations. In these two equations, we must find x of s and y of s. We must find x of s and y of s. We can use Cramer rules for finding it. We can use Cramer rule for finding x of s and y of s. You also can use elimination or substitution to get x of s and y of s. You can get y of s from this equation. Y of s is s minus 2x of s minus 1, and replace to the second equation. Then you can get x of s and y of s. But here I'm going to use grammar rule. Grammar rule for this one, we just take the coefficient of x of s and y of s. We just take the coefficients of x of s and y of s to be the matrix of A. So matrix A, I'm going to remove these to write down the matrices here. We say A equals s minus 2, then minus 1. The coefficient of y of s is minus 1, and the coefficient of x of s is s minus 2. And the coefficient of x of s here is minus 3. And the coefficient of y of s here is s minus 4. That's it. Now, we find ax and ay. What's ax? Ax, we replace the first column, as you see. The first variable here is x of s. We replace the first column by the right hand side. The right hand side here is 0 and 1, and b, which is the right hand side, is 0 and 1. So 1 and 0. We replace the first column by the right hand side to get ax, which is 1, 0, negative 1 is minus 4. And ay, we replace the second column by the right hand side. We get s minus 2, minus 3, 1, 0. Now we find the determinant for each ax and ay. For each ax and ay. The determinant of a is s minus 2 times s minus 4. Multiply these two, minus, we multiply these two. Okay, it's s minus 2, s minus 4, minus 3. This is determinant of a. And you can simplify it more. It becomes s minus 2, s minus 4 is s squared minus 6s plus 8. Plus 8 minus 3 equals to s squared minus 6s plus 5. Okay, and now we can say it is s squared minus 6s plus 5. And this equals to, we can make it into two brackets. It is s minus 5, s minus 1. So this is the determinant of a. Now we should find determinant of ax and determinant of ay. Determinant of ax is multiplying these two minus multiplying these two. Multiplying these two in this direction. I mean, multiplying in this direction. It is 1 times s minus 4, s minus 4. Minus multiplying in this direction, we get 0, because 0 times 1 is times negative 1 is still 0. And you can just write down s minus 4. And the determinant of ay equals multiplying these two is 0, minus multiplying these two. Here we have a negative sign also, we get 3. These are the determinant of ay, determinant of ax, and determinant of a. We now have determinant of a, determinant of ay, and determinant of ax. We say x of s equals determinant of ax dividing by determinant of a, and y of s equals determinant of ay dividing by determinant of a. This grammar rule, you studied this, is it? Now we replace ax is s minus 4, s minus 4 dividing by s minus 5 times s minus 1. And here this equals to 3 dividing by s minus 5, s minus 1. These are x of s and y of s. This is x of s and y of s. And here we find the Laplace inverse for both sides. We get x of t and y of t. X of t and y of t are the solutions for the system of differential equation. We now take an example. Okay, we take an example here. We have this example as a system of differential equations. In this differential equation, in this system of differential equation, we are asked to solve the system by using Laplace transforms. And here we have given the conditions: x naught, which is 0, y naught is 0, is 1. So x of 0 is 0 and y of 0 is 1. We follow the steps. First, we take the Laplace transform for both equations. The Laplace transform, so here we can say it's x prime. You can say it is x prime equals minus x minus 3y. And this is, we can say y prime equals minus x plus 1. Okay, we take the Laplace for each equation. The Laplace of x prime equals the Laplace of minus x minus 3, the Laplace of y. This is the Laplace transform for the first equation. And the Laplace transform for the second equation, y prime equals the Laplace transform of minus x plus the Laplace transform of y. Now we take the Laplace transforms. The Laplace transform of x prime, the Laplace transform of x prime is x s times x of s minus x naught equals the Laplace transform of minus x, it's minus x of s minus 3. The Laplace transform of y is y of s. So this is the Laplace transform for the first equation. And for the second equation, it's the same. We said the Laplace transform of y prime is s y of s minus y naught equals minus x of s plus y of s. We have these two equations. We now rearrange the equations. For the first equation, before we do that, we insert the conditions. We replace x naught, this is x naught, and this is y naught. X naught is 0 and y naught is 1. We replace x naught by 0 and y naught by 1. So here, this becomes 0 and this becomes 1. Okay, now we put all the x of s and y of s terms to the left hand side and other terms to the right. Here we get we are going to do it here. Here we have minus x of s, we move to the left. Minus 3x y of s, we move to the left, because these are includes x of s or y of s. Here we go, you get s x of s plus x of s plus 3y of s equals 0. It equals 0 because in the right hand side we have nothing else. And this is 0, we move to the right hand side, it's still 0. And we move this one, this negative one, to the right hand side. And moving these two terms to the left, we get s y of s, s y of s minus x minus x of s becomes plus x of s. Y of s becomes minus y of s equals 1. It's negative 1. When we move to the right, becomes positive 1. It's plus 1. This one becomes plus 1. We now have these two equations, and then we'll write down it again. We have x of s and x of s. The common here is x of s. What's left? S. plus 1. We get s plus 1 times x of s plus 3y of s equals 0. This equation 1. And therefore, equation 2 here we have s y of s and minus y of s. We get s minus 1 y of s. So let's write down x beneath x. Here we have x of s plus s minus 1 y of s equals 1. This is equation 2. We have these two equations. We work on these two equations. Here, up to now, we just took the Laplace transform for both sides, then we rearranged. Now, we apply the Cramer's rule for finding x of s and y of s. For grammar rule, we should find A, matrix A, which is the coefficients of x of s and y of s in both equations. For the first equation, the coefficient of x of s is s plus 1, and the coefficient of y of s is 3. In the second equation, the coefficient of x of s is 1, and the coefficient of y of s is s minus 1. This is A. What's AX? We replace the first column by the right-hand side. In the right-hand side, we have 0 and 1. So the first column becomes 0 and 1. We replace by 0 and 1. We get 0, 1. And the second column is 3 and s minus 1. In matrix A, we replace the first column by the right-hand side for AX. And for AY, we replace the second column by the right-hand side. We get s plus 1 and 1. Here, we get 0 and 1. These are A, AX, and AY. Now we find their determinants. Determinant of A equals, to, it's s squared minus 1 minus 3 is s squared minus 4. This is s squared minus 4. Okay? And determinant of AX equals minus 3. Determinant of AY equals s plus 1. These are the determinants. Then x of s equals determinant of A dividing by determinant of AX dividing by determinant of A. This is x of s. This equals to minus 3 dividing by s squared minus 4. And y of s equals determinant of AY dividing by determinant of A, which is s plus 1 dividing by s squared minus 4. Okay. We now try to find the Laplace inverse for these two. We say x of s equals minus 3 over s squared minus 4. And y of s equals s minus 1, s plus 1. It is s plus 1 dividing by s squared minus 4. Okay. Now, here we say x of t, we take the Laplace inverse for both sides. For both. Here, the Laplace inverse here, and the Laplace inverse here. The Laplace inverse for the left-hand side becomes x of t. And the Laplace inverse for the right-hand side is minus 3 over s squared minus 4. We say the Laplace of sine hyperbolic of, it's hyperbolic, yeah. Let me check. It's hyperbolic or sine. It's hyperbolic. We say the Laplace of sine hyperbolic of AT equals to A over s squared minus a squared. This is sine hyperbolic, and this is the Laplace of sine hyperbolic. But here we have s squared minus 4 in the denominator, and in the numerator we have minus 3. So in the numerator we must have 2. We must have 2 because this is a squared, so we must have a in the numerator. That means we multiply it by 2 and dividing by 2. X of t equals minus 3 over 2 Laplace inverse of 2 over s squared minus 4. And this equals to minus 3 over 2 sine hyperbolic of 2t. This is sine hyperbolic of 2t. And then for the y of s, we take the Laplace inverse for both. The Laplace inverse of y of s is y of t. Equals y of t equals the Laplace inverse for this fraction. We can separate, or you can give in the numerator we have 2 terms, and in the denominator we have s squared minus 4. So we can separate the fractions. We can give the denominator for both terms. It's the Laplace inverse of s over s squared minus 4 plus 1 over s squared minus 4. Okay, so y of t equals the Laplace inverse of s over s squared minus 4 plus the Laplace inverse of 1 over s squared minus 4. Now, this is cosine hyperbolic inverse. This is cosine hyperbolic inverse. It's a cosine hyperbolic, it's cosine hyperbolic, not inverse. It's cosine hyperbolic of at. Its Laplace is s over s squared minus a squared. So this is the cosine hyperbolic of 2t. Y of t equals cosine hyperbolic of 2t. And this is sine hyperbolic, but here you must multiply it by 2 and then dividing by 2. And we get plus a half of sine hyperbolic of 2t. Okay, we multiply it by 2 and divide it by 2. This is y of t, and this is x of t. We say x of t and y of t are solutions to the system of differential equations. This is the solution. In solving a system of differential equation, we just need to find x of t and y of t. We first take the Laplace for both sides. Then we rearrange the equations, putting all x of s and y of s in the left and other terms to the right. Then we solve these two equations that you get by using Cramer's rule. After finding x of s and y of s, we just take Laplace inverse for both sides. That's only 3 steps. It's only 3 steps. That's enough for today. We have 2 more examples for tomorrow.